So today I'm going to be talking about the Pascal's method task, and there are three methods involved in that, which is the drawing our roots method, which is going from simple to complex, the Pascal's method, and lastly the combinations method, which we learned in the previous unit. Now to begin, drawing our roots is simply just drawing a diagram to find out exactly which ways we will get the total possibilities. So it's very simple, and basically we just draw out whatever diagram we have. So here we have a 4-square diagram, and to get from point A to point B, we draw each method from getting from that point to that point. And you can see that we get 1, 2, 3, and then 4, 5, and finally 6. And that basically shows us that we have 6 total ways to draw roots, and that's the total roots we have. It's pretty simple, but it can only be used for the simplest diagrams. So we can also pick other points on this route of how to get there using the routes we've already drawn. So you see that we have point C right there, and there would be 2 ways to get to point C, because you can only see from point A to point C that we've drawn those lines to get there. Also, you can see that if we add up that there's one way to get from the left, one way to get from the right, we would get a total of 2. And basically we can do that for all the other points on the square as well. So totally we have 2 points. So basically it seems pretty simple, and it is really easy, but the thing is that it doesn't always stay this simple as 4 squares. We'll come across some problems that are 9 by 8 or have a total of 82 ways. We occur with such problems, and we can't possibly draw all of them. We could try, but the thing is that's not necessarily efficient. So the best thing to do is use a different method, and that's where other methods come in. So basically, you're right if you say that you can't do them, but the thing is that it doesn't mean that you can't do it. It means you can still do it. But Pascal's method would tend to be the easier way to solve the problem, and that would be shown later on with the Pascal's triangle. But drawing our roots no longer works, and that's where we can see exactly when to use drawing our roots is when there is exactly a small number of total ways, and we can predict that based on how many points we have on our diagram and how many intersections are open. So how many points will lead us to the final answer in total. So the best way to use drawing roots is when there's a few number of squares or total roots. So here's an example of when we should use this method. So Tammy is someone who wants to go to her friend's house, and she lives at a distance of 3 blocks north and 2 blocks east. So already we can see how the distance and diagram should look like. So how many possible ways are there for Tammy to get to her friend's house? Now we can see that there's going to be a square involved in this, and we're going to see from point A, which is Tammy, to point B, which is her friend's house. But the problem in this scenario is that there's going to be an intersection which is close to her right. So the point to Tammy's right is going to be a point which is going to be considered 0, so you can't pass that point. And here we can see that that point right next to Tammy that's marked red is a closed intersection, so it won't be used to draw. So we draw the first route, and then there is another route, and then another, and this continues till we've drawn all the routes possible. Once we've done that, we can see that this resembles the diagram that we drew before. It's almost exactly the same because we closed an intersection. Those 2 squares at the bottom weren't necessarily used. It was just a point from T to F. So it was exactly the same as 4 squares. So this reminds us of the previous diagram we drew both ways. But what do we do about the diagram that was too complicated to do? Well, this leads us to our next method, which was Pascal's method. And that is basically the more mathematical way of solving for the problems. So this reminds us of Pascal's triangle, which is a well-known triangle, and basically it has many patterns, and it shows us ways in which these patterns can apply to real-life applications and situations. So here we can see that it's 1, 1, 1, 1, 2, 1, and the triangle continues. And the pattern in this triangle is that the two previous terms add up to the next entry in the next row. So basically we see that 1 and 1 makes 2, 2 and 1 makes 3, and etc. So basically that's how we find out where the numbers come from. So as we continue, we can see that it's addition involved to find the next few terms. So how can this help us solve problems? Well, addition of the two entries to find the next row creates a sort of pattern that can be involved in the same diagrams that we used before. See, it took 2 points to get to the next point. We had 2 options. You either go left or you go right, and you take a right turn or you take a left turn. So those 2 options can add up to the next term, which is similar to Pascal's triangle. So we can also see that the row number is synchronized with the entries in that row. So row 3 has 2 3s in it, row 2 has a 2 in it, and the way we can use this for problems is basically that it allows us to use the same very complicated and hard to draw diagrams with calculations now. So here is an example of a more complicated looking square or rectangle, and it has 2 points as we did before, but we can't draw all the ways there because it'll take too long. But as you can see, from the corner of A to B, we start seeing that there's one way to get to A to the next intersection, and then we start adding the previous 2 terms, and we get 2, 3, 4, 5, and we keep on adding the previous 2 terms, and we can see at an angle that it creates the Pascal's triangle. But the number that we get at the end at point B is basically our total number, which is quite simple because it allows us to know efficiently what the total possibilities are. And there is a Pascal's triangle. So this is more mathematical because we have to keep on adding every previous term, but it creates the Pascal triangle in such a form that the complicated diagrams are easily shown. So let's try an example and see how we can use that in this method. So Alex owns an apple farm, and basically he wants to gather 4 apples, but he has to have 1 apple from each row, and he can't take more or less than that, and he can't go back. So if he's taken 1 from 1 row, he can't just go back and take something other. And basically, if the apples are stacked in an equilateral triangle shape, then how many possibilities are there? Now already when you say equilateral triangle, we can imagine sort of Pascal's triangle. And because you're taking only 1 apple from each row, you can kind of see that there's going to be a route to go through from top to bottom. And because there's 4 bottom apples, that means there's going to be 4 different possibilities for each bottom apple taken. So if you take the first apple, you'll have this many possibilities. You take the second, you'll have this many possibilities at the bottom. So obviously we're not going to draw out all the possibilities, but you could if we were using drawing roots and it was pretty simple. But as you can see, we used Pascal's triangle and we found the total number of possibilities for each apple. But the thing is that that's just for each apple. We want to know the total amount because he could choose any of the bottom apples. So we can add up 1, 3, 3, 1 and get 8, and that gives us a total of 8 possibilities. And this leads us back to the Pascal's triangles that we drawn before. But another method that is pretty simple and gives us an entry very easily is the combinations method that we learned earlier on. So as we know, combinations is NCR with N and R subscripts, and it allows us to choose a specific number of objects from a specific number of objects stated before. So as we know, we do n factorial over n minus r factorial times r factorial, and that would give us what the possibilities were. But here, let's draw Pascal's triangle and see if that works. So we have our regular Pascal's triangle and the number of rows that synchronize with it. But as you can see, each number in Pascal's triangle is an entry, and each entry has a specific type of identification, which is which is the row number and the entry number, and none of them are ever the same. So as you can see, that would be entry 1, entry 2, and there is entry 0 because 1 is considered entry 0 at the beginning of the row. So each of these have this sort of code, which is T, and then the row number, then the entry number. But that can also help us know exactly that can help us put it into a combination formula. So let's try an example with that. See, we have 3c2, which was basically 3 factorial 3 minus 2 factorial over 2 factorial, and that gives us an answer of 3. But if we were to do it with Pascal's triangle, we can see that it would be 1, 1, 1, 2, 1, etc., and that the row would have to be number 3, and the entry would have to be number 2, and you can see that also equals 3. And if you do it with the diagram, because it's pretty simple to do, so we're using all 3 formulas here, we can see that it will also give us eventually a number of 3, because it is row 3, entry 2, which is quite similar to the one above. And basically combinations allows us to put it in the formula we already know, which is quite efficient, but it gives us a total number of possibilities for that exact entry up till that entry. So it doesn't help with necessarily the same diagrams that we did with Pascal's triangle, but it does allow us to know when we can efficiently find out the total number in one entry. Therefore, all these methods of drawing our roots, Pascal method combination, are quite different, but they're all used in key ways. And that's what allows us to efficiently know what type of total possibilities there are in different contexts.